In this video, we are going to be beginning our module on the stoichiometry of gases. The learning objectives for this entire module are to apply stoichiometric relationships to calculate the amounts of substances and apply that concept of stoichiometry to gas law calculations, and then also do calculations involving Dalton's law of partial pressures. Before we can begin, we do need to talk about gas evolution reactions. In our previous module, we were talking about how we can apply this double displacement reaction pattern in order to predict products of a chemical reaction. If we do that for this reaction here, we can split acetic acid up into H+ ions and acetate anions. And then sodium bicarbonate, which is baking soda, can be split apart into sodium ions and then hydrogen carbonate anions. When we apply our double displacement reaction pattern, sodium will bond with the acetate. That's a 1 positive and 1 negative, and so that forms sodium acetate here. And then the H and the hydrogen carbonate anion come together and they form hydrogen carbonate, H2CO3. That's their ion exchange product. But the problem is H2CO3 is not stable. And so this molecule spontaneously decomposes into water and some carbon dioxide gas. So instead of writing this balanced chemical equation including H2CO3, we need to write it as instead water and CO2 as products. When you mix baking soda and vinegar, which is acetic acid, together, you see these bubbles naturally come up. And so they're making a little volcano using baking soda and vinegar. So this just happens. They break apart. And baking soda is not the only thing that gives rise to gases when it reacts. If you see any of these products here in this table, these 4 products in this table, you need to recognize that these will form gases. The first one is H2S, and this one doesn't decompose. This is just H2S. So the gas that forms, if you see H2S here, H2S is just a gas at room temperature. These other ones all have oxygen. And so that's how you can remember whether it's going to break apart or not. All of these ones do have oxygen as one of the products, and it's going to break apart into water and some gas. The chemical formula for the gas that's evolved is shown here. And so you can see that in the products, that's the gas that's written, and water is a liquid. So all these ion exchange products don't include these in your chemical formula. Instead, recognize that it breaks apart into water and some gas, and then write the chemical formulas for water and the gas that's involved. If you can remember that these polyatomic ions break apart into water and some gas, you can actually figure out the chemical formula of that gas by doing a little bit of mathematics on this chemical formula. For instance, H2SO3 has 2 hydrogens and 3 oxygens. If I subtract out water, which has 2 hydrogens and 1 oxygen, I am left with no hydrogens, and I am left with just 2 oxygens. So my product is SO2 gas. For my next one, H2CO3, if I subtract out 1 water, I'm going to be left with 1 carbon and 2 oxygens. If I take NH4OH, ammonium hydroxide, and subtract out H2O, I am left with, I'm just going to subtract both of them from there. I do combine these H's so that is NH3. There's 1 nitrogen left and a total of 3 hydrogens left. So that's NH3. So this gives you your chemical formulas of those gases. So just recognize that these break apart into water and some gas, and then you can figure out what the gas is by subtracting the water from that chemical formula. Let's do a practice problem. Go ahead and try to apply your double displacement reaction pattern to these sets of chemical reactions and see if any of these release gases. Go ahead and pause the video and work these out in your notebook. Unpause the video when you're ready to check your work. Okay, so let's go over this. We have H plus ions, NCl minus ions, Mg2 plus ions, and hydroxide 1 minus anions. So the magnesium will bond with the chlorine. I'll need 2 chlorines in order to make a neutral ionic compound. Checking my solubility rules, magnesium chloride is soluble in water. My other product is HOH, better known as H2O, water. I need to balance this equation. I have 2 chlorines, so I put a 2 here. That gives me 2 hydrogens, and I got 2 more hydrogens, so I'm going to need 2 waters. 2 oxygens, 2 oxygens. So now we're balanced. Now for our second one. We have Pb2 plus and S2 minus. Sulfur is right underneath oxygen, so it shares that common ion charge with oxygen. And then we have H plus and sulfate ions. Sulfate ions are 2 minus anions. So I'm going to pair the hydrogen up with the sulfur, and that is H2S in order to be neutral. And then PBS. PbSO4. Now let's check those solubility rules for PbSO4. PbSO4 is going to be insoluble, so that's going to be a solid. And then H2S is one of those gases that we're supposed to recognize from the previous page. So we do have a gas evolution reaction. And now let's go for this next one. This is nitric acid. Nitric acid is composed of H plus ions, NO3 minus ions, sodium ions, and then hydrogen carbonate anions. Splitting these up, doing our double displacement reaction pattern, we have sodium nitrate, which is going to be aqueous according to my solubility rules. All nitrates are soluble. And then I have H2CO3 as my other product. This is going to break apart into water, which is a liquid, and some gas. Subtracting water from this chemical formula gives me CO2 as my gas. So those are our balanced chemical equations.